right, and I presume that I have P6 over MMM symmetry. Okay, I'm happy with that. I finish. So I have the symmetry, and I want to solve the structure. So I have profile fitting, I can extract my intensities, and I want to solve the structure. Formula. I don't really know what the formula is, but I don't worry, because I don't need the formula for the solution. So I just type the names of the atoms, just so that the picking procedure can assign tungsten to the heaviest peaks and lanthanum to the moderately large, and so on. So I just type the types of the atoms. This is X-ray data set, so I keep the calculation, the parameters default. And in this case, I take the risk, and I really use random starting phases. So I hope that it will work. It works almost always. Actually, always. And I start Superflip. That's it. So that was the Superflip part, and now back to Jana 2006. No, not quite. I would like to spend a few minutes on the log file of Superflip to show you some of the most important information that you can see there. So you can see a Wilson plot. From powders, the Wilson plot is not always very reliable, but if it makes a nice, well, this is a nice straight line. So, of course, these scattered points are the Wilson plot values calculated from the data, and the small dots, this is the linear fit. So this is an indication that you have at least somehow reasonable data. The next table is the coverage. Well, in powder diffraction data, you have 100% coverage up to the highest resolution that you choose. And in this case, it's really high resolution. So the coverage is not a problem for powder diffraction data. Now I recall I didn't comment on coverage for the electron diffraction data, but for this data set, the coverage was about 95%. So it was fairly complete data set. Then we have the iteration part, and after 140 cycles, you see a message, calculation successfully converged. If you see this message, it means that the program believes it found convergence. Nothing more, nothing less. Sometimes, if the program does not see the convergence, it can still be there. So it's worth checking the result even if you don't see this message, even if the maximum number of cycles is reached. So that's, it's always worth checking. And the next part deals with the symmetry. So here you see a label checking the density for symmetry. And this long list, long funny list, lists you all possible symmetry operations that you can have in the lattice. So in hexagonal lattice, the list is very long. You can have threefold axis, mirror planes, C-glides, A-glides, screw axis, and so on and so on. So the program takes all possible symmetry operations and calculates a sort of R value, so reliability value, how well is the space group, the symmetry operator present in the density. And here you see a beautiful jump from something that gives an R value of 0.3%, so very low, up to here, up to the twofold axis along B, and all the rest is 45 or more. So you can see that these first, I don't know how many, 10 or so, symmetry operations are present in the density, and the rest is absent. And if you have international tables in your head, you can see that this corresponds to 6 bar 2C. If you don't, the program has them not in its head, but in its code, and it can make the guess for you. And here you see that the Hermann-Mogen symbol that's suggested is P 6 bar 2C, although we said our initial guess was 6 over MMM. So now we see that we made a mistake with the symmetry. So we discard the result because it's incompatible with the symmetry that we had. We change the symmetry to P 6 bar to C. And we run the calculation again. Oops, okay. There is a little, not really a mistake, but something unexpected. If you run it for a second time, Jana puts automatically 10 attempts. This is not actually what it should do. We have to correct it, and I forgot to switch it off. So now we will have 10 calculations instead of 1, but luckily it doesn't take 2 days, so we can wait for the 10 calculations to finish. And Superflip takes the one that it considers the best. So we have, again, the same space group is predicted. That's not surprising. And now we can accept the result. And we have a solution, and again, we view the solution with Vesta in 3D. So again, you could see that there were nicely round peaks, so no problem with that. And if we zoom a little bit, the green spheres are lanthanum atoms, or are peaks that were interpreted as lanthanum atoms, and the gray spheres are tungstens, red are oxygens. And well, it's difficult to say just like that the structure is correctly solved, but you can see that it's quite uniformly populated with the heavy atoms. If I switch the model off, it's actually a clear picture of a solved structure. If we concentrate on the oxygens, we see that there is a couple of them. For example, these 3 here, they coordinate a tungsten atom, so they are most probably correct. Some of them are missing, and there is a couple that are false. And these are, how much time do I have? No time anymore. All right, good. Well, we are essentially finished. So what I would do is I would delete the oxygens, I would refine, and we would get an R value of something like 5%, and the structure would be finished in about 2 minutes from now. But I won't do it. It is, again, in the tutorial, and so you are welcome to try it on your own. I thank you for your attention, and sorry if I talk too much.
I told Lukas he had no time left, so that we still have 5 minutes left for questions. So now it's up to you to support me. I need some questions.
Yeah, there.
Yes. Yes.
Sorry.
Mark from Edinburgh. The question was, you said the Superflip doesn't use the input symmetry, but does it consider whether the structure is centrosymmetric or not? Because this affects whether what phases you can have as random starting values for the Superflip algorithm. Or
No, it makes no assumptions about the centrosymmetry.
okay. So it starts with completely random phases, and if they end up being plus or minus 90 at the end, then that tells Superflip that it has an inversion center.
Yes.
Yeah, okay.
Yeah.
Oh, thank you.
Henrik from Stockholm University. I was thinking, let's see, in order to avoid excessive overlap, if you have a problem to get Superflip to converge, is it a good idea to use excluded region at the higher 2 theta?
To some extent, yes. If you have a total overlap, if you have just, essentially a continuous band of peaks, then they don't really bear much of information for the ab initio phasing, so you can throw them away. It does not really harm too much if you don't throw them away, but it's a good practice to remove this if you have really strong overlap. That's true.
Sven Holmell from Stockholm. You mentioned there in the beginning about the contents of the unit cell. So you put 3 atoms, lanthanum, tungsten, and oxide, and I think you said it was said there would be 3 of them in 3 sets of those in the unit cells. You would think that the program would expect to find 9 atoms, but it has no problems at all to find about 100. My question is, does it help if you make use of the volume? If you say every atom should be 20 cubic angstroms, you could easily think there would be about 30 of those, and then it should look for 90. But it seemed it did it itself. I don't understand.
Yeah, so of course, if you have some information on the composition, it always helps to use it. So in a clear case like this, the fact that there were 3 formula units, that was just an artifact, that was the default value suggested by Jana. I didn't change it. So Jana didn't make any assumption about the number of atoms. He just looked at the peak height and thought, okay, this is high, this will be tungsten, this is low, this will be lanthanum, and so on. You can use EDMA if you have qualitative composition and you know the number of atoms. So then you say, I have 300 atoms in my unit cell, and please distribute them between tungsten, lanthanum, and oxygen. That's a medium, moderately strong assumption. And if you are confident about the composition, you can say, this is my formula, I want this number of atoms, this number of oxygens, and this of tungsten. So you have these 3 options. It's up to you how confident you are about the composition, and also how good quality data you have. So in the noisy electron diffraction data, it really helps if you know the composition. Although you can do it even without, but it helps.
Okay, but in this case, when you just said you have these 3 elements, will the program then automatically, let's say, the strongest third of the peak is lanthanum and then tungsten, then oxygen, or will they sort them in some, how is it doing it?
The program integrates the charge around each peak and then scales it, compares the charge, the integrated charge, with the atomic number. You find the best scale, and then you say, okay, this, after scaling, this charge is closest to lanthanum, so it's likely to be lanthanum. This is closest to tungsten. So it's using the integrated charge around every peak.
Thanks.
Hi, Paul from Sheffield here. If you don't have high resolution data, but you do have heavy atoms, will you find the location of those heavy atoms?
High resolution data, that depends on your structures. So what is high resolution for organic structure, or for heavy atom structure is can be low resolution for organic. So I think you would this would work if you cut your data at 2 angstrom. That would almost certainly work, and probably it would work even at much lower resolution.
That takes us up to coffee break. Before we go, I'd like to first thank both demonstrators from this morning.